In this video we're going to talk about the fundamental theorem of calculus part 2. Essentially, how do we use the antiderivative, which we proved in the last video would help us find area. How do we actually use that? We're going to do some more examples here. Find the average value. First of all, well, remember, average value follows this formula. Let me just write it on the bottom here. 1 over b minus a multiplied by the integral from a to b of f of x dx. Remember, what we're doing here, if I can kind of just remind you over here, is we're saying that if I know the area of a that I want a rectangle to have, and I know what its base is, how do I find the height? Okay, I'm just going to put a little underline. How do I find the height? And the answer is you divide by the base. Well, that's what we're doing here. We're finding the area that we want the rectangle to have with the integral, and then we're dividing by the width of the base, which is simply the difference between the endpoints. So like for this very first one, we'd have the integral 1 over 3 minus 0 multiplied by the integral from 0 to 3 of x squared minus 1 dx. You could evaluate that with fn int. We could actually do it now with the antiderivative. The area comes out to be 6, so it would be 6 divided by 3, which would be 2. Okay. This next one would be 1 over pi minus 0 multiplied by the integral from 0 to pi sine of x dx. Well, we've dealt with this a lot. Remember, this was that whole investigation we did the other day. This was, the answer here is just 2, the area, so it'd be 2 divided by pi. That'd be the answer. And finally, the absolute value of x minus 3 from negative 3 to 10. Well, I put this one in here because as we start to move away from using geometry or Riemann sums to evaluate integrals, and we begin to use calculus, the absolute value is one spot we still may have to use other techniques. And the reason is there's not a good algebraic way to deal with absolute value, so there's not a nice calculus way to deal with it. So we will have to either use geometry and graph, or we could use fn int. That area comes out to be 15.5. You know, if we actually do it, so it'd be 15.5 divided by 13. You could type that in and get a decimal answer for that. So in the other video we talked about how we could use antiderivatives to evaluate area. We set up a relationship that said if we took the derivative of an integral, we got the function. And what that meant was that derivatives and integrals had to cancel out, meaning they had to be inverses. Well, we know what the inverse of a derivative is. It's the antiderivative. So the antiderivative and integral must be tied. We must use the antiderivative to do the area. Now, all of that leads to this. If a function is continuous at every point, and big F is its antiderivative, then to find the area of little f of x, we find the antiderivative and evaluate at the right endpoint and the left endpoint, and then simply find the difference. And we began talking about that in the last video. So the area under x cubed plus 1 on the interval, well, 0 to 4 x cubed plus 1 dx. So we find the antiderivative. It's 1/4 x to the 4th plus x. We're going to evaluate that at 4 and 0. Remember, that vertical line means evaluate, and we're evaluating at both. If I plug in 4, I get 1/4 4 to the 4th, which is 64 plus 4. If I plug in 0, I get 0 plus 0. Remember, I find the difference The answer here is 68. And that's it. That's the area from 0 to 4 under this curve. Next, we're going to evaluate an integral set up by f of x equals sine x with that interval. So this time we'll go from 0 to 2 pi sine of x dx. Now, I just want to quick, if I can, do a little sketch here of that, what this is going to look like. Hopefully you have some inclination to think that the answer here should be 0, because this positive area that we know is 2 and this negative area that's negative 2 will cancel out. So the antiderivative of sine x is negative cosine x, evaluated at 2 pi and at 0. Well, the cosine of 2 pi is 1, so negative cosine of 2 pi is negative 1. The cosine of 0 is 1, so negative cosine of 0 is negative 1. So this does come out to be 0. Now, I do this problem, both of these really, to show you that the integral represents displacement. You know, if you think about this as a velocity graph, you say, well, it went forward 2 units, then back 2 units, its displacement was 0. That's what the integral tells us. X cubed plus 1 is never negative. You know, if you sketched a graph of it from 0 to 4, it's always positive, you know, from 0 to 4, so we didn't have to worry about it. But let's say you didn't want displacement. Let's say you wanted distance. What would you have to do? Well, I'm going to do that example next, but I just want you to think about the fact that the integral just gives us kind of that overall change. How far are you from where you started? And the answer for this would be 0. If you wanted the total distance, of course, that would be 4. So the question is, well, how would you handle that, especially by hand? Well, let's look at that. Find the area bounded by x squared minus 4x plus 3 in the x-axis. Now, this word bounded, you know, this is basically, again, giving us that distance idea. It's saying how much total area is there. In the previous example of sine x, you'd say, well, there's 2 positive units and 2 negative units for a total of 4 bounded units. Even though the integral is 0, there are 4 bounded units. So this bounded idea, you know, if I could do this on my calculator, I'd just say, well, I'm doing the integral from 0 to 5 of the absolute value of x squared minus 4x plus 3. Okay, and of course, graphically, what the absolute value does is it just knocks this up like this to be positive, and then you wouldn't have to worry about the part that's negative. It would just find all the areas and combine them, which is what you want. But if you were going to do this by hand, you'd have to set this up as multiple integrals. And the first thing I guess we'd need to do is factor this and say, well, it's x minus 1 and x minus 3. Okay, giving us these 2 points right here. So then I would need to do an integral from 0 to 1. I would need to do another integral from 1 to 3. Notice that this integral would give me the negative area. And I would need to do one more integral from 3 to 5. And what I would need to do then is actually evaluate these and come up with the answers. And this, of course, would be positive. I'm just going to put like a little plus, you know, blank. This would be negative, blank, and this would be positive, blank. And I would need to then ignore that negative. Okay, I would just need to ignore it and basically make them all positive and just add them up to find the bounded area. And that would give me the distance. Okay, I'm not going to do that for the sake of time, but that's how I would do that bounded area.